Well, let's wait for another couple of minutes before starting. So, um, hopefully all of you have seen the homework that we handed out. And there is also appendix to lecture 10, which Louis recorded. So it kind of walks you through some of the software you can use to analyze the binary. In any event, on Thursday, Louis will walk you through the homework. So it would be good if you try to download stuff and all and just familiarize yourself with the various pieces so that you can ask questions meaningfully on Thursday. Anyway, so that's on the logistics side. For the presentations today, so I sent around the order. Stick to the 9-minute threshold that I had given so that we finish in time and also have some room for question or two. So we can start with the first one. And at the end of every presentation, it would be good if you can just move on to the first slide of the next one so that
hello everyone. My name is Anne, and this is Eugene and Katin. And our midterm presentation is going to be on keyboard snooping. So what is keyboard snooping? It's a side channel attack in which the attacker recovers what a user is typing through audio and etc. What we're going to try to do is do that with a smartwatch, which has an accelerometer and a gyroscope, as well as a stereo microphone. So given those features, we will try to identify specific keys, which leads to identifying passwords, identifying tasks, and the first three will be performed on a physical keyboard first. But if we achieve success with the physical keyboard, we will try to perform everything with a mobile phone as well. So I'm going to describe the anatomy of a key press in terms of audio. So whenever a user presses a key, there's actually two peaks that are formed. One is when the user presses the key, and the other is when the key is released. So with most power works, use the first peak because that's louder than the release peak. So we'll take that peak and then perform FFT and then feed that into a classifier which has all the different, which returns the different keys. But these methods require knowledge of how of the features of each different key. But what if we don't know what the keys sound like? So what we will try to do later is perform k-means clustering on the key features, and then use a dictionary or language model to figure out the most probable letters. And then for task identification, which is like when the user is emailing, chatting, gaming, etc., we're just going to use a basic neural network classifier. So for the data sets, we're going to start simple. We will have the user type numbers repeatedly, and then move on to a combination of letters and numbers. And then for the task identification phase, we will just have the user perform these three tasks: emailing, gaming, and chatting, for a long period of time. The idea is we need a huge data set for adequate accuracy. For the platform, we're going to use the wearable sensor app, courtesy of a professor's lab, Nestle. And those wearable sensors for the Android Wear smartwatch and the phone, they communicate through Bluetooth. And then we will also use a stereo microphone, a separate one. We did try using the built-in laptop microphones, but the audio wasn't very clear. For processing, we will use Python, and for training and inference, all the machine learning stuff, we will use Keras.
Okay. For our current status, we have done First, the literature reviews in the field of keyboard animations and sensor fusion. And since we need a huge amount of data, so it is very important for us to have some tools to assist our data collection. So in past few weeks, we've been working on 2 Python programs. The first program is for automating the data collection. It will instruct the subject to type something like one line by line, and this, automatically do the audio recording and control of the Android watch, and also log the keystroke. And after we get the data, we need to process and synchronize them. For example, if we have a sample of like 2 minutes, and we have maybe have tens of samples in that period, we need to find a peak to synchronize them and normalize all kinds of data and split them into groups. So that's what we are doing now, and we almost finished. And that's it.
Excuse me.
So for our next steps, we're going to record ourselves with tasks such as emailing, gaming, and chatting, so that we can expand our data sets. And after that, we're going to implement our neural network or language model on our data set to basically try to train and test the model and see if we can increase the accuracy for our keystroke prediction to a certain threshold. And furthermore, for our future work or any optimistic goals, we're going to try to compress the model, since currently we're doing it on our MacBook. And for that, for our research to be usable onto an embedded system, we wish to compress the model and implement it on an embedded system.
Any questions?
Anyone? Questions? I have a couple. So did you already try to see if the different keys sound different, in the sense on your audio side, do you see that the keys have different acoustic signatures?
So currently we only tried using the microphone on our MacBook, and basically the keys all sound, they're too similar.
They sound the same. Okay.
And so we're trying to look into more sensitive microphones.
Yeah, so that's the point why we use the accelerometer data, and also we use stereo microphone. So maybe the location matters.
So, but what about the prior work? What like in prior papers? Did they find significant difference? Some.
I think for the previous papers, it works fine for some keyboards. Yeah,
For
but
some
not.
keyboards.
Yeah, but nowadays, since the keyboards are not this different.
Like, do they comment on why do the keys sound different? Like, okay, so I can see that some keys are bigger versus smaller, like the space bar will probably sound different than the regular keys, but all the vast majority of keys which are of similar size, why would they sound different, I guess?
I think one point is maybe there are some tiny difference between key, and another point is maybe the user have different behaviors when type different keys.
So we punch stronger keys closer to us,
Yeah.
or something like that?
Yeah.
Okay. But you haven't noticed any difference?
Since we haven't started model training.
Cool. No one else any questions? We move on. Thanks.
Thank you.
All right. Hi, everyone. I'm Andrew. This is Mrinal, and this is Kian. Our project is on floor mapping and activity prediction from passive infrared sensors in smart homes. So the kind of goal of this project is to look at these passive infrared motion sensors that you could have in smart homes, like for security systems, for tracking when people are present in a room or not. These have some applications also in ambient assisted living where they're used to monitor elderly people and to keep track of where they're at and to help assist with their quality of life. The idea behind these in terms of privacy is that instead of video, there's no actual like inherent information gained about the people that are in a set system with these motion sensors. So then it's thought to be more private, but then what we wanted to look at was how, like what other information you can learn from just knowing when these sensors fire. So there's a lot of previous work we were reading about these networks of motion sensors in homes that are used to track where people are and focusing on the placement of the sensors and maybe some hardware optimization of them for tracking specific activities. But then what we kind of wanted to look at is just knowing the times of when the sensors go off and which ones fire in a given apartment or home, what we could learn about the inhabitants from that. And part of the inspiration was that Wi-Fi sensing paper from earlier in this quarter where they're snooping on the packets and we wanted to do a similar thing with these motion sensors in place. And then in terms of specific goals for our project, basically knowing which sensors fire when, just based on like unencrypted network traffic from a network of these motion sensors to figure out what we can learn about the people, the inhabitants in the home, and the room placement of each of the sensors. So to try to infer based on the timing of the firings or the sensor triggers and how often they occur, basically to learn something about the smart home setup and possibly learn more about the activity patterns that go on.
So our technical approach, we're going to use something called OpenSHS, which is basically a smart home simulator. It allows you to interface with this blender, which you can see here, and you can actually create your own smart home with different smart devices. And what we want to do is we're going to create a bunch of these similar smart homes with different sized floor plans, different rooms, and we're going to use that to do supervised learning to essentially figure out what kind of room we're in and do this project. So OpenSHS already provides a wide variety of sensors. They have door sensors, light sensors, pressure sensors on the bed, on the couch, that kind of thing. So what we're going to do is we're going to combine these sensors into a single unified sensor, which will basically simulate the motion sensor that would be in each room. And what we can do is we can actually place an actor in the scene. So let's say we start them outside the house, and then we can run through a typical day in the life in the daytime or the nighttime where they're going to the bathroom, turning lights on, turning lights off. And what Blender and OpenSHS will do is they'll aggregate the data and basically give us multiple days of data just from that one run. So they'll kind of randomize things, move things around, but in the end we get a pretty robust data set. And we look to collect data at different time margins. So maybe we can assume that 1 minute is long enough for them to move from room to room. But ideally we would extend this and actually have a more interrupt-based approach, because we really only need to see when a sensor is firing, and then when it fires in a different room, we don't need to see necessarily how long and every single sampling. Okay. So the time series data will basically be binary values for each room. And to make it easy, when we begin, we're going to use just a single actor in our simulation. And we can definitely determine the adjacent rooms from the sensor data, and we want to find patterns within this data to predict the rooms. For features, we can use time values and duration and how many times during the day that sensor was triggered for some of our features. And we're looking into two approaches right now. One of them is a hidden Markov model, where basically the different states, the rooms would be a state change, so moving from one room to another would be one of the edges of our model. And another approach is to use random forest. So it's an ensemble method that utilizes decision trees. And each room, we would build a model that would be able to predict this multiple classifiers and try to actually determine what room we're in based on this time data. And prior literature has used similar things, random forest, in this case a 2-layer random forest, for activity classification. So a little bit different, but they used similar sensors for their project.
So currently we are creating like smart PIR sensors for the OpenSHS framework. And we're gonna know which rooms they're in, so we'll have labeled data about like this sensor belongs to this room, like bathroom or I don't know. So the OpenSHS framework is what we use to gather the data. It essentially like spits out the CSV with like a bunch of where every row is like a timestamp, and then you have a binary value for if the sensor was on or off during that timestamp. And for each sensor it'll be a different column, so we'll know like which room, like which sensor went off in which room. The one issue we have found is that some of the objects in the publicly available repository are like kind of lacking, and so we'll have to implement our own objects in this simulation framework, and that's what we're working on right now. And the other thing we're working on currently is to find out which machine learning algorithm is like appropriate, whether it's the Markov model or the random forest. So yeah, we're trying to figure out which one of those two are better suited for our data set. For the next steps, we will, once we decide which model is better, we'll have to implement it, hopefully using a library. And we want to use a simple supervised learning model, not something super complicated which requires a lot of data like a neural net. Then we need to train it, obviously, and once we do that, we'll have to create multiple different smart homes with different layouts and gather data on simulation based on those. And then we need to create a simulation to run inference on, so like figure out if our model works or not. And if like our stretch goal is maybe be able to do this for multiple actors, like simulate multiple people living in the same household and see what kind of like information we can learn from that. There's obvious challenges to this because now we have, like, if two people are in the same room, like that might just go off as one trigger as opposed to two different triggers, and just figuring out like which model might be, if our model still works or if we have to change the model. And we also had to figure out how to do multiple actors on the OpenSHS, in the OpenSHS framework. That's it.
Questions?
Comments, concerns?
Any other questions? So, just to make sure, you're going to be trying it out on a totally different home layout than the one you're training the model on, right?
Yes.
Okay.
Yeah.
So, I don't quite understand
Wait,
why.
what do you mean by
is,
totally different? Like,
like if
The
I mean,
floor plan will be
Or like
different, the
floor plan
balcony
is
is different.
different.
Arrangement.
but I don't think we're going like crazy, like, oh, we trained it on like a 1-bedroom layout and then now we'll try it on a mansion kind of thing.
Yeah, but at least some perturbation.
Yeah,
Like in the sense.
Yeah.
So what will you be changing? I mean, I guess at some level, if you were to say, okay.
So our goal is to like train it on different home layouts,
Uh-huh.
and then figure out like let's say we have a 2-bedroom layout, and like to get to the kitchen you have to go through like the hallway and then the living room, and like that could be one layout, or like you have some other layout with a similar room number setup, and then I guess like to run our inference on, we'll
I mean, it seems to me you are underplaying the value also the time of day, in the sense that we don't use, use bathrooms in morning but not at night. We use kitchens, right?
Yeah.
I mean, different rooms also have, it's not simply the order in which things happen, it's
Right.
also
Mhm.
when things happen.
Yeah.
Right? And those are signatures of the rooms, in a way,
So-
and they port across households of different sizes, right?
Yeah.
Right,
I mean,
yeah.
So for our random forest, we're using the time data as one of the features. So let's say if the bathroom is used between 8 a.m. and 9 a.m., then there'd be a 1. That'd be a binary column. Whereas the rest of the day, if they're not using the bathroom, then it'd be 0. So that's going to be part of our features for the random forest. For the hidden Markov model, it's more difficult to add that time data in. So right now, I think we're leaning towards random forest at this point
Okay.
because it'll give more depth.
And what did you mean, in one of your slides you said not every object is there or something like that? What was that?
Oh yeah. So
What objects are you referring to?
so like these units, like the sensors themselves, like
Mhm.
they're implemented as some sort of Python script
Mhm.
to work with the OpenSHS framework. And the repository that they have open sourced has very few of these objects.
Yeah, I think they only have like a door sensor or something like that.
Yeah.
Oh,
So
they
we
don't
need
have a motion sensor?
Yeah,
they
so we
don't.
basically need to-
we need
yeah.
to implement it.
Okay.
Yeah.
So in your picture of the simulator, I see a lot of furniture and stuff. Are those objects essential to your project?
No. We're not going to be. We're going to have one motion sensor per room, so it's not essential. But I mean, walking around the objects, doing different things, interacting. You might, in our simulation, you might stay longer in the living room because you can sit down and watch TV or something like that. Whereas in the bedroom, you can interact with the objects, but they're not essential per se.
So it looks nice. Yeah.
So when you say multiple actors, you're saying as if there's multiple people throughout the different rooms, and trying to check which rooms have presence of person in them?
Yeah. Also
Yeah.
determining how many people live in that home would be the end goal there.
Okay.
Yeah.
So why would multiple actors cause problems?
Because I think it's more difficult to get the training data. I guess we could have different, training for 2, 3, 4 people.
I mean, to me, it seems like a room is distinguished by type of motion and when the motion happens,
Mhm.
not so much how many people are there.
Mm-hmm. So that's exactly why it'd be hard to determine how many people are there.
No, but if your goal is not to determine how many people are there, if the goal is simply to again
Determine the-
determine the placement of the sensors, that should not be impacted by if your model
Yeah.
is applied to a household which has a different number of individuals.
Mm-hmm. That's true.
Yeah.
We're talking about the multiple actor is an extension. If we're trying to figure out how many people are there. If we have
Okay.
multiple
Yeah,
people,
right.
we should be able to collect data regardless. But
Okay.
one of our goals is to actually determine how many
How
people
many
there are.
people.
Yeah,
Right.
it wouldn't be any harder. Although we need to make sure that it'll actually work in Blender.
Yeah.
Because right now, when you simulate the person, you're walking around in the house,
Mhm.
and then we need to figure out how to get 2 different
Two
people to walk
people.
around and do their
It's like a
own.
first-person game. You're almost playing, interacting
Yeah.
with the house and moving around.
Yeah, but that should be possible.
That's the strict
I think
for
you can
initial,
you can
yeah.
simulate it twice.
Yeah.
Okay.
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 Next. Just go over there.
Hi there. So our project is on side channel attacks using differential analysis. So a little bit about our project overall. We're trying to improve on the research accomplished by a team that did the work in the floating point multiplication time attack on deep neural network. Essentially, they were able to look at an image that was processed through a neural network and identify the input image it was a simple black and white image, so we're looking for ways to improve on it. But before being able to do so and replicate this project and then improve on it, we needed to establish some basics. So a couple aims that we had overall was just to understand power analysis and how to find traces and things associated with that. From there, identifying patterns. That included identifying for loops and multiplications because those are prominent in neural networks, as well as recreating the results mentioned in the paper, and then from there, improving on it and making changes to the project. So the technical approach. So we first started with understanding the basics, understanding power analysis and the tools needed to. So we were introduced by the professor to Chip Whisperer. So Chip Whisperer includes some hardware as well as software for power analysis and just taking traces as well. It's really cool. We've been using the Chip Whisperer Nano as well, which is a hardware put together already for Chip Whisperer that kind of makes it easy to learn and go through some of the tutorials that they have so you can learn and understand their API. So that's been another thing that we've been learning is their API and understanding how to take traces of these differential measurements, as well as being able to graph and plot them and then start to be able to analyze them. Another thing we've already kind of looked at is the oscilloscope called a picoscope. So we just got familiar with that, how to set it up, make sure we're ready for that. So that one we haven't actively used so much yet. We've been focused on the Chip Whisperer and the Chip Whisperer Nano. Otherwise, the Chip Whisperer has a processor that's pretty slow. So if we do need to upgrade, we're already set up to use a Raspberry Pi combination with the picoscope for oscilloscope use.
In terms of actually identifying power traces, what we would do is we would write our firmware for the STM chip that was included on the Chip Whisperer Nano. We would upload that firmware, and then we would collect a power trace after turning it on and try to identify things such as for loops and floating point multiplies. This is essentially important because when you're trying to reverse engineer this neural net, you're going to need to figure out and identify the exact places that you want to figure out where that multiply and accumulate is going to be happening, because otherwise you won't be able to figure out or reverse engineer the image that is being fed through that neural net itself. And we essentially obtain traces back like this. So as you can see, there's a noticeable delay at two certain points that correspond to the beginning and the end of the for loop, which allows us to figure out where the for loops, of course, would be taking place. And going further with the trace analysis and actually looking deeper inside of the individual for loops, the floating point computation on the processor has different power traces, whether or not you have a multiply by 0 or a multiply by a non-zero value. 0 multiplications take significantly less time, and as a result use less power. So as you can see in the diagram here, the multiplication by 0 is significantly shorter than all the non-zero units, as multiplied by 1, 2, 3, and 4 are about 160 time units on the axis, whereas the multiply by 0 is only 120. And this occurs regardless of where the floating point multiply occurs. So taking this further and doing a floating point accumulate or floating point addition followed, or floating point multiply followed by a floating point addition with the multiply and accumulate, we get these chunks of traces on here. Let me see if I could move. This first chunk here is pretty consistent throughout all of them. It's this one's the different one. This is the multiply itself. So it's a shorter. When it's shorter, it's a 0, and when it's longer, like in this case over here, it's a 1. And then it's followed by this accumulate that always takes about the same amount of time, regardless of what it was accumulating. So this gives us the ability to actually identify when a 0 pixel value was being multiplied or when a non-zero pixel value was being multiplied. And since we're working with a black and white image, that will let us perfectly recreate the image itself, which is pretty valuable. That was pretty much what we've gotten from the trace analysis so far.
So yeah, as stated before, we're able to determine the input, but we're not able to determine the exact input. So this is one of the major shortfalls of the papers we were replicating. So it could either be the input or the weight of the neural network to be 0. From there, you're unable to distinguish which one was the cause of the multiply of 0. Another problem is once you identify which one is the 0 input, you can't figure out what was the exact value. So in this case, if it's a black and white picture, you can't figure out what was the exact intensity value for that input pixel. So we've been able to, to summarize, we've been able to understand the Chip Whisperer API thoroughly, so we're able to capture traces and then look at the data and also do some computation on it to figure out what was being done in those traces. And for our next step, we're ready to transfer to the Raspberry Pi and bare metal Raspberry Pi, because for the Chip Whisperer, as stated before, it has limited memory capacity and processor capacity. So it is hard to fit a full neural network onto a Chip Whisperer Nano. And for our next steps, we're currently deciding what improvements can be made on the paper. So maybe as a hint from the previous paper, their problem was that they were unable to identify the exact intensity of the pixel value. Maybe we could probably do something on that. And so we'll be dedicating these next 3 weeks to be focusing something novel and contributable for this paper.
Questions, anyone? So what portion of the neural network you actually put onto the Chip Whisperer Nano?
We pretty much put on the weights. The Chip Whisperer Nano is like limited to like 5K of data, so we only were able to put about one image or one row of one image on there just to do like initial testing. So we put the weights and values for just the first row rather than the entire thing, because the entire thing caused it to run out of RAM, which is unfortunate. But
and it was using, like, your code uses floating point arithmetic there, or?
Yeah, floating point
Yeah.
arithmetic.
Within the firmware file.
Okay, great. Thanks.
Okay, hello everyone. So the title of our presentation is P2I, Privacy Preserving Inferencing for Medical Cyber Physical Systems. So private data, in particular medical data, so this type of data entails a lot of utility. However, this also includes a lot of privacy concerns. For example, if some external party wants to compute some inferences on this privacy sensitive data, then the parties which are hosting the data might be unwilling to provide the third parties all of this data because of the privacy concerns. So a good example might be, for example, suppose that the World Health Organization wants to find out the global outbreak of flu and all of the countries in the world. However, each of the countries wants to keep their data secret. So the main question is, how do we perform this sort of collaborative computation in the context of medical cyber physical systems without leaking the privacy sensitive data to competitors? So there are two ways we can do this. So firstly, the first thing that we might do is secure multi-party computation. So in secure multi-party computation, what we do is we encrypt the data. And on this homomorphic data, we divide this data into chunks and send them to several computers or sensor nodes. They do some computation and then just send us back the statistic that we want. And another method to do it is known as secure aggregation. So in secure aggregation, we also do the same computation on homomorphic data. However, all of this is done within a central entity inside a particular organization. So the challenges in SMPC and secure aggregation are scalability, computational issues, and implementation issues. So most of the SMPC and secure aggregation protocols that are present currently, they have all been just simulation results and designed with the notion of a trusted third party in mind. For example, some sort of cloud service. So what do we want to do? So our goal is to implement secure aggregation and SMPC protocols on the edge devices. So we don't want any third party to come into play. And we want to scale down all of these protocols so that they're able to run in resource constrained settings. Basically, we are not designing our own protocols. We're taking all of the existing protocols that are secure on the information theoretic point of view, and we want to benchmark them in terms of the performance, privacy, and security metrics. And our main goal is to reduce the computational overhead in all of these protocols that are present. So Vivek is going to present the attack model now.
We can actually have a similar attack model for both secure aggregation and multi-party computation. So what we assume is that in secure aggregation especially, what we assume is that the aggregator is semi-honest. What that means is it is honest, but it is curious to know the sensor data. So, and also all the other sensor nodes are again honest, but they want to hear each other's data. And we can also assume that these nodes are later on malicious nodes, or even the adversary is malicious, by just tweaking in a little bit and having the main server. So the secure aggregation is essentially that you have a two-tier hierarchy. So the highest hierarchy can communicate with the sensor nodes directly. That would actually make sure that even the aggregator can be a adversary. And in case of secure multi-party computation, we don't have a central entity. It's all distributed among the systems. And again, the adversary model is they are semi-honest and curious currently, but they can be malicious at a later point. And for malicious, we can actually use something called zero knowledge proofs, which actually is used for authenticating the sensor nodes directly without knowing any information content about the nodes. So this is like the approach what we have taken for the secure aggregation. So we have a two-layer security that we are doing. So a layer directly with the sensor nodes. First, the data is encrypted using a homomorphic encryption, and this homomorphic encryption is common among all the sensor nodes, but each of them actually use a different random number to obfuscate the data. And over this, we again add a AES kind of encryption, just so that each of this AES actually is provided by the aggregator to the sensor nodes. So each sensor node's data is inaccessible by the other sensor nodes who can actually hear the radio link. And the adversary can be anywhere in the network. The main goal of the adversary is actually to eavesdrop on the data and try to know what the raw data is. So what we do is first we encrypt the data at the sensor nodes using homomorphic encryption. Actually, the first step is the queryers send a query to the aggregator. The aggregator tries to figure out what the query is, and it also can send some homomorphic data like weights, which actually is used by the aggregator to compute a statistic over these sensor nodes. So this sensor nodes encrypted data is merged with the encrypted weights or parameters from the queryers and combined at the aggregator and send it back to the queryers. So we have actually implemented currently mean, convolution, linear regression, and vector sum over Berkeley's temperature data set, which has about 50,000 odd points. And we have like 100 clients and one single aggregator and one single querier right now. We have implemented this, and roughly these are the specs as of now. So the main constraint, as we can see, is the time taken for the key generation. So we currently are generating this on a single platform, but later on we need to decide who will be generating the key. So maybe one solution is that the queryers, who are actually the servers, can generate these keys and give it to all the nodes directly initially, and then the aggregator can be put into the system. Another thing is that it doesn't take too long to actually encrypt or decrypt the data, so this can be done at any sensor node. So we can also assume that the query nodes can be sensor nodes, and like this can completely take place in the same system, because even the addition multiplication doesn't take too long, and even like this is all resource constraint that we can do. And the homomorphic encryption we are currently using is the Palayer homomorphic encryption. So that's it.
Yeah, so while the secure aggregation protocol assumes that there's like a powerful aggregator within the organization, in secure multi-party computation, we assume that all of the sensor nodes or data hosts, like they're going to take part equally in this homomorphic process. So basically, we're using a platform known as ShareMind for implementing secure multi-party computation, and the protocols we chose. So there are three protocols: ABY, Shared 3P, and SPDZ, each with its own merits and demerits. So basically, what you can see is that in secure multi-party computation, so suppose that all of these sensor nodes are also the queryers here, and suppose that one of these sensor nodes wants to like know the mean of some data. So basically, it floods the request to all of the sensor nodes in a homomorphic manner, so that all of the sensor nodes also don't know like who asked. So basically what the sensor nodes do is, so basically they collect their own data and then they basically choose which of the sensor nodes might want to compute. So usually in secure multivariate computation, randomly 3 of the sensor nodes are chosen to do the calculation on a distributed level. So this, for example, suppose these 3 sensor nodes were chosen and they do some sort of inferencing, for example, maybe finding the mean of some sensor data or doing some linear regression or something, and then they flood all of their individual results to all of the sensor nodes as well. And then all of the sensor nodes, through the protocols that I have shown, they combine the data and then they get the results. So the main challenge in SMPC is that, as I have already said, like all the implementations that I've seen in literature, they focus on large scale systems. So we're trying to like scale it down for edge devices. So here are some of the functions that we have implemented, like shuffle, quicksort, regression, simple statistical parameters and such. And we have actually benchmarked our implementation on a Raspberry Pi environment in the virtual box. And here's the time that it takes for scalar addition and scalar multiplication for these 3 protocols. And on the right hand side, you can actually see the code that we wrote inside the virtual box. So for implementation, we're planning to do it both in a real-time simulator environment as well as hardware environment. So for the real-time simulator environment, we're using something known as the mininet. So in the mininet here, there are a couple of data hosts, and these are like the computational nodes, or the nodes that are going to like do something to the data. So we're creating these sort of structures, and we're going to implement the aggregation and the SMPC protocols that we've discussed. And not only that, so we have managed to actually install ShareMind on a Raspberry Pi platform, though these SMPC protocols, they're not actually supported on AMD processors, but we have managed to work with ShareMind and we have implemented it in Raspberry Pi. So basically, instead of just doing it on a simulator environment, we're also going to later show like what are the real-time benchmark performance metrics on hardware as well. So overall, the current status is as follows. So basically, we have finalized which aggregation and protocols we're going to benchmark, and we have some preliminary benchmarking results for our aggregation and SMPC. And we have also finalized the simulator environment that we'll be using, as well as the hardware environment. And we have also implemented, as I've shown, several oblivious custom operations that are like all homomorphic. So the next step is like we need to design some more operations and aggregation, some more operations for aggregation SMPC protocols. And we're going to actually implement all of this in real time in the simulator environment, the RPi, and we're going to see how it performs, like, if we consider it like a hard real-time system. And last but not the least, we'll try to tune the parameters to reduce computational overhead as well. Thank you.
Great, thanks. Question, anyone?
Yeah.
For these different aggregation steps, you use Python for the key generation?
Yeah, so we actually used the normal encryption AES we have not done AES exactly right now. We have used the Palier homomorphic encryption library, and we were also shocked about this when the key is actually generated. The library also hides the process behind the scene. So that is actually the generation of the key, and that part is very secure by the library itself.
So would it be faster if we use like KRC, or does the library already use like a SUI?
But yeah, as Professor mentioned earlier, like if we use our own this thing, we might miss out on the edge cases. So we have not tried to implement our this thing, but I guess it is already quite optimized.
I think it should be quite similar.
Yeah.
Because I implemented SMPC in a language known as secrecy. So it's like very close to C language. And like if I consider like the environment he was using and I'm using, like there's not that much of a difference, because the compilers that these things use, like they don't use normal C or Python compilers. They have like special compilers to do all of these tasks. Yeah.
Were there previous works for doing SMPC and aggregation on edge devices, or is this kind of?
So most of the stuff that I've seen in literature, like they have provided like the mathematical description that they're going to do something, and they have like provided the computational complexities and stuff like that, but none of them really show like what it's gonna be like if it's gonna be implemented. So recently I have saw one group from Berkeley. So they're like designing their own SMPC protocols for edge devices. However, like they have not, like those protocols, like they are not yet entirely secure from information theoretic point of view. So like the protocols that we've chosen, these are like proven mathematically that this will be secure under certain conditions.
Okay, great. Thanks.
Hey folks, I'm Jennifer and this is Daniel, and kind of following on that same theme, our project is the cost of private computation, so looking at homomorphic encryption implementation on low swap platforms. Swap being size, weight, and power. So our overall project goals and specific aims, we wanted to compare encryption performance parameters on a polynomial data example versus unencrypted computation to get a baseline for what a low swap SoC device would do. We also looked at doing it on Amazon Web Services as a secondary examination. We wanted to report performance metrics for various homomorphic functions using the Sifl library, simple encrypted arithmetic library, developed in 2015 by a group from MIT. And then we wanted to make recommendations on whether it's practical to use homomorphic encryption on a small swap platform. Okay. So our technical approach was we wanted to implement this initially on a DE10 Nano SoC. It's an Intel product with a Cyclone 5 FPGA. It's also got a dual-core Cortex-A9 ARM processor. So we looked at this, attempted to implement the Sifl library examples on this board, and found that we were woefully underpowered for this kind of board. And we chose this initially because it's something commonly used for CubeSats and other small satellite devices. So we thought, is this practical for this kind of device? And as a motivation for that, we're looking at specifically SpaceX's launch of the Starlink satellites and their vulnerabilities. So current status part 1 was we attempted this and were woefully unsuccessful, in part because the processor we chose is a 32-bit processor and the libraries were incompatible with that. It does work locally, and we transitioned then to the Amazon Web Services portion of our attempts.
Yes. So since the low-powered board was essentially too small to be able to handle this library and doing these kind of computations, then we are wondering, okay, so that's obviously this lower bound doesn't work, and we're looking into also, okay, in terms of FPGA implementation stuff, but you would essentially need an extremely expensive, like I think 8,000 or more type of FPGA to be able to even try.
It's like ultra scale class FPGAs.
So essentially the lower and mid tiers of FPGAs wouldn't be able to handle it. So now we're looking, okay, if those can't, where can we go? If we continue going up the chain, where eventually can you start using these libraries? So we wanted to look at, okay, if we're running kind of like some AWS instances, so we can try a bunch of different instances and hopefully see where's the lower bound, what's kind of the comparisons between these in terms of performance. So the lowest one that Amazon has is like 0.5 gigabyte RAM micro instance. And then we're gonna also look at, okay, if you're gonna kind of do like a client server model in terms of with two different instances, comparing them and see if, okay, even if like the lower end can't handle it doing it entirely by itself, then maybe can you offload that to a more like expensive server, and does that kind of implementation work? So we're looking at still using that Sifl library, which is what we found to be the most like reputable library in the space, and trying to basically create a benchmark and a platform to be able to see like the CPU utilization and the computation time for both performing these kind of computations locally, and then also for performing them using some kind of like client server model. And so we were able to get some instances running, get some examples running using this library, and kind of we can see that there definitely is performance differences based on the platform we're running it on. And so now kind of the question we're trying to explore is how much can we improve it by instead, is there can you actually implement this client-server model where the client is a much lower powered device. Because even with this library, there's a lot of overhead even just to create the keys and create the initial encryption that then you send the encrypted version to the server and get back. So kind of seeing what's the limits for that and what kind of platforms can this realistically be run on and what kind of speeds can it be run at. So we're currently working now we've run it, set it up on 2 different instances, and now we're running to basically trying to create a more extensible platform. There wasn't, at least that we could find open source, any kind of this client server benchmark kind of platform for doing these kind of testing. So we're going to try and build that so we can kind of add to the community, so other people can add on to this. And so that's what we're currently doing, is working on that implementation of this kind of more extensible platform for testing, and then looking to run those comparisons and get some more kind of practical advice for what kind of platforms can run these encryption, the homomorphic encryption libraries.
So I don't quite understand what exactly is the limitation with the ARM? Is it the fact that it's 32-bit or memory size or what?
It's a little bit of both. We think that we can pare down, the libraries are C++ libraries. We think that we can pare down some of the functions if we were running on like an A53, which is 64-bit version of that, but we kind of were dead in the water at the start with the 32-bit processor.
So like, I was wondering, did you try like a Raspberry Pi 4 or something like that? Because if you're running it on a micro instance on AWS, it's already a lot less memory than what Raspberry Pis have.
Mm-hmm. Right.
And Raspberry Pi are all 64-bit, and so.
Yeah, so I think it was.
I don't know about your Yocto, the other board that you're using.
It's in
the bottleneck exactly.
At least for even with the small instance, it actually can't run with certain of the larger. So there's a couple of knobs that you're playing with this library. One is called like the polynomial modulus. There's like a coefficient modulus and a plain text modulus, and so those are different knobs you're playing with. Even some of the larger polynomial moduluses can't be run on the small instance because the bottleneck is the memory.
Okay.
So even just if you take the cipher, the ciphertext data structure they have, and you serialize that, it can be like even like millions of bytes long. It's like huge, even just for just the way this library is set up. So I think the bottleneck, at least that for the instances we're seeing, is the memory. I'm not sure what it was for
the platform is just a fundamental incompatibility.
No, the reason I brought up Raspberry Pi is that's what 8 gig or 16 gig or something like that, right?
Yeah.
Okay, so that's comparable to actually your higher end of the AWS instance that you're using, and it's 64-bit, right?
Mm-hmm.
Yeah.
So why not try that?
I
we
guess
can do that next.
We definitely could.
It's gonna work on that, right?
Sure.
I think it's gonna work. I think the main limitation is the 32-bit, 64-bit thing.
Yeah.
Because like we also initially had a 32-bit OS and our protocols are also not working. Then we switched to a 64-bit environment and then
So yeah, we could switch platforms and try that too.
Try that. The reason why we went to AWS just to try that was just because it would be very easy to spin up a bunch of different instances and compare them, but we're definitely open to trying another platform.
Mm-hmm.
So we could look at the Raspberry Pi.
Yeah. Cool.
Anyone else with questions? Okay, if you want, thank you.
All right, hi guys. So I'm Hamza, this is Zach, and our project is combating the vulnerabilities of split learning. So we're going to talk a little bit about background, what are some distributed deep learning methods, what is split learning, and what are generative adversarial networks. We'll talk about our goals, our approach, status, and then future work. So currently some distributed deep learning techniques, there's federated learning. So essentially if you have like a machine learning model, the way this works is you can distribute this to multiple clients by basically having a central machine learning model, and then the client will download the model and run any data through it and basically give all the model weight updates using its local data, and then give that to the central server to aggregate. And then there's large batch synchronous SGD, which is basically which is similar. So what we're actually working on is split learning, which is basically a variation on that. Actually, it's a new technique since last year from MIT. So basically, the way it works is you have part of your model on a client and part of your model on a server. And so there's actually 3 variants to this. One is just your standard part of your model on the top, On the bottom, you have the server on the left side. On the right side, you have a vertically partitioned, which is basically different clients have different subsets of data, like different types of data. What we're focusing on is actually in the middle, split learning without label sharing. So what this gives you, basically part of your model in the very beginning, your input data is actually protected from your server, and you also have your output. Your labels are also protected, basically, because the very end of your model is also on the client side. So the server knows nothing about either your input or final data. And so to give an idea of how this works, basically, your client has some public layers that are known to every client in green, you can see at the top. And then the data and the labels are all owned by the client, so they're not known by anybody else. And then the private layers are on the server. This, no one but the server knows, and so it could be any type of model basically in the middle. And then the way it works is you basically, like a normal neural network, you do a forward pass that goes through, starting with the client, and then it goes through the server, and then the server passes it back to the client. And so once your forward pass is fully done, your back prop works the other way, like normal, basically goes through the client, back to the server, and then back to the client. And so basically the benefits for doing this technique is this is shown to be having higher accuracy with less client-side computation. And this is partly because the front and the end of your neural network, like the beginning and last few layers, typically have fewer parameters than the middle of your neural network. And this also has lower computational bandwidth. And then finally, this gives additional privacy, because in addition to having private input data, you also have private labels. And then also your server-side model architecture isn't really known by any of your clients. It's just known by your server. And so that's a lot harder to attack than if you know your entire model, such as in federated learning. And then the other bit of background we wanted to give is on generative adversarial networks, GANs. So basically, this is a network that works like a two-player minimax game. So you have basically two networks that are training off of each other. First, you have a generator that tries to generate some data, and then you have a discriminator that tries to tell whether that data is real or fake. And so the way this works is one of them generates data, the other one discriminates, and they train off of each other until the generator can generate really realistic data. And so that's what a GAN is. And so the overall goal of our project is first to basically simulate a baseline split learning technique, and then present some of the vulnerabilities of split learning. This is like label poisoning attacks, backdoor attacks. These are things that have been used in federated learning and with other types of techniques, but haven't really been applied to split learning since it's relatively new. And then also we're looking at some methods such as like black box Trojan detection and mitigating like some of the federated learning poisoning techniques as well, but this time on split learning, basically to make it a lot more robust. And so some of the experiments we're working on, first we want to show that we can approximate the black box model. So the black box model is essentially your server, since you don't know what model is going on in there. On the client side, you can possibly approximate that server as a black box. And we're showing how we can do this with models of various complexity and accuracy. And next, we can also optimize this black box model approximation using some gradient patterns, such as like patterns during your training. Next, we're looking at GAN label poisoning, basically using a GAN to use some label poisoning techniques that have been used in federated learning as well, and then use gradient techniques possibly to improve the GAN performance as well, and then some other attacks such as backdoor label poisoning, and then finally we'll evaluate attack detection and prevention mechanisms basically to prevent some of these attacks. And so to first talk about the black box approximation that I mentioned, we're working with the MNIST digit classification. And so essentially, looking at our server as a black box, we can try it with different types of networks with a different number of layers. For example, we can have like 1, 5, or 9 different CNN layers as our model. We can have different filter depths and different dense layer widths. And then we're trying to approximate this with models of different complexities, because we don't actually, as an outsider's point of view, know how complex our black box model is. So basically what we're going to try to do is use our GAN with different models of different complexities to basically model our black box server and then see what the effect of that is.
And then we have our GAN poisoning attack. This is the main meat of our project. In our research has been shown that this could be most detrimental to split learning. We're going to be performing this with MNIST, CIFAR, and the AT&T classification data sets, and we have an 8-step process that's inspired by a federated learning GAN poisoning attack, but we have to add extra steps because we're dealing with a black box model. So in this 8-step process, we have our split learning model here, and then we have our discriminator and generator as the GAN. So in the first step, we train just like normal with the normal split learning method. We're basically pretending to be a normal client. Simultaneously, we train the GAN to continuously generate better and better fake data. Then we push the fake data into the split learning model. We append it with the input data, so it goes through our split learning model, and we save the labels from the network here. And then we perform one back. Then we perform a normal backprop step, kind of still pretending to be a regular client using the input data we had appended to the fake data. Then using the black box labels we have, we can refine this part of the discriminator to estimate the black box portion that we don't know, that's private on the server. And we do all this process until we get really good images and fake data generated from the generator. Finally, to commence the attack, we generate fake data from a trained GAN. It goes through our system, and then we finally poison the labels and perform back propagation on these poison labels to affect some other client's data training. So our current status, we have shown that we can approximate the black box model. I'll show results for that next. We're in the process of performing experiments 2 through 4, and we will wrap up with experiment 5 once we finish those. So the results of our first experiment, was to approximate the black box model. And we've learned 3 things. This is the discriminator complexity, this is the black box accuracy, and the color is how well we're able to estimate or approximate the model. If you have a discriminator with much low complexity, you can't hope to approximate the black box model. We couldn't get anything out. As long as the discriminator has enough complexity, it didn't matter how complex the discriminator was, it mattered on how accurate the black box model was. For example, if there was a lot of loss in the black box model, it was harder to estimate. And finally, we were able to decrease loss with an increase in discriminator complexity. So we can be more certain with a higher complexity in the discriminator. So that essentially shows that we can approximate the black box model. So for our next steps, we're going to continue performing experiments 2 through 4 and wrap up with our final experiment on how to mitigate this attack. Questions?
Questions, anyone? So, I'm still not sure I fully understand the attack model out here. Okay, so what's the attacker trying to achieve out here?
The attacker is trying to, if you could go back to the diagram. The attacker is trying to go unevaded by poisoning a label that they're not associated to. So in this case, this client is training on, say, labels 2 and 7 in the data set. The GAN is going to estimate labels 0 and 1. And then we poison the labels by generating data from 0 and 1 class, and then we mislabel them and train the network on those mislabels. And in that way, our labels 2 and 7 remain unaffected, but other clients become attacked and affected in the system.
I see.
And in this way, we're actually able to go unevaded because there's no way for the server to tell that the backprop is malicious.
Cool.
Great, thanks.
Let's go through that. Had a lot of extra slides. There we go.
Okay, so everyone, today we'll present our topic for the project. It's the same body authentication. So our project goal is aiming for handling the data security and privacy issue because of the pervasive use of the IoT wearables and mobile phones. So basically in settings like healthcare, so even for like training. So you will have a lot of wearables on your bodies, and potentially there might be persons nearby you also using the same wearable just like you did. And there might be cases that when you take off the wearables, just possibly the other people mix up with your wearables, and then you will accidentally access their data. So the results about that is that you will potentially get the data you from the other people's, as well as like getting a lot of authentications complications. And so to simulate that situation, we try to aim for the cases that whenever that you have your wearables that it's out of your reach, so basically you cannot interact with them. And in order to do the authentications, we will aim for gathering context-aware data that will be able to identify that whether the wearables and your phone are still within your reach. And our end deliverable will be an Android authentication app that's able to do both the initial pairing as well as the continuous periodic verification. So again, this is like an overall architecture about our app. So for sure, it will first do the initial pairing between the target wearables and your phone. And once that connection is established, then it will enable the sensitive data you want to record it. And as time goes on, then the app will tell the users what triggering events it will be used in order to initiate its periodic verifying phase. And the users should be able to respond to such events so that both the phones and the wearable will record the target context data. So then we were using the recorded data and compare if they are similar to each other. And basically it will constitute to the evidence on whether these pair devices are still within the user's possessions. So this is like our very simple initial pairing scheme. So basically, it's just like a typical pairing that we will establish such relationship, and then the user can start having the data communications.
So for this setup, we do have 2 stages for the initiation and for the connection to the sensors to make sure that it is exactly on the same body for the same user, especially for the healthcare applications and like day-to-day applications in the IoT systems. If we want to make sure that the device is specific to that user and like a specific user in a household is using that sensor, we have to have like an initial pairing with the signature for that specific user, and then periodically check with the user to make sure that it is exactly on that same person. So with our process, with the initial stages that we have been developing so far, we were able to develop different Android applications to be able to receive the sensor data, such as the accelerometer, gyroscope, and like heart rate data from our phone and the wearable, and sync the data between the 2 devices and plot it out for the visualization and tracking to see how is the data or like the acceleration changing over the period of the time where it is on body. Also, same story for our earballs. We were also working on that, and then we integrated the sensors for real-time sensor and data acquisition. Right now, we're working on the implementation of the pairing conditions, so then we can actually pair up all the devices together at the initial stage. And then we're investigating the interrupt detection algorithm that is looking for like the interrupts in the sensor setup, and I will walk you guys through how this whole process works out through our method. So for the first stage, it's like the watch is in the idle mode, which it's not establishing the data connection to the phone, and it is then like you have your phone actually receiving the data from the watch. And then after the data is actually established, then you have like the data streaming from the watch to the phone. So then we actually have here, if we have the accelerometer and the gyro from the phone itself, and then from the watch itself. So now Ria can tell you more about it.
So the wearable is actually having the gyroscope and accelerometer data, and we're tracking the same from the phone to see how they correlate. Right? And as you can see, these are the 2 signals, and this small arrow that you see, this was an interrupt that was detected when the watch was removed from the hand. And that's precisely what we want to work on, detecting these interrupts, and based on that we will it will be validated whether it's whether the wearable is strapped onto the person or not, and that's when we will disconnect the devices. And at the wearable side, we're also getting the IMU data, the accelerometer as well as the gyroscope values, because we're using the phone, wearable, and wearable, and trying to see whether they are on through these values we're trying to ascertain whether they are on the same person or not. We'll also be implementing speech to text recognition in order to which can be used for some kind of authentication, especially during the initial phase, to ascertain whether it's this particular person whose values have to be recorded. And finally, we also created the application that would store all the data for further analysis, whether it's for comparing and using it for authentication, or even the heart rate or the medical data that is used for analysis. So we're going to store it in a text file in the Android phone. And we've created different applications, and now we'll be working to integrate all these applications to form one app. We also need to combine the hearable as well as the wearable to see how they're working together, and how they can actually validate the sensors being on the same body. We especially need to work upon setting up the checkpoints where the periodic authentication would take place. So the initial pairing, first would be the initial pairing that will take place every day, and then we'll have various checkpoints at which we will do periodic authentication to make sure that it's the same person. And finally, after the whole app is integrated and we create one single application, we'll test the whole system to see if it's working or not and finalize the report. These are some of the references that we refer to for our work.
So to clarify the whole system, the initial pairing, we will have it based on like the user's like name. So then we have that a specific signature for the user using it. And then for the wearable, we do have the specific signature of that user. So then we detect that initial pairing. Then throughout the day, throughout several hours, we check for like if the velocity of the person, for example, is changing during a motion. So if the sensor results are out of sync, then we will detect that motion, that change in the motion. So then we will disconnect the whole syncing of the sensors. Other than that, we will keep receiving the data for the person.
Yeah. Any questions?
Any questions?
Anyone question? Okay. So I'm still not quite sure which problem you are solving here. Are you solving the problem that there's a wearable and a phone on the same person initially?
Yeah.
Yes.
And you're continually testing that are they still on the same person?
Exactly.
Yes.
Right.
The original one?
Yeah.
Mm-hmm.
That's
Or
That's-
that the variable has moved on and see, you talk about the interrupt and all. I could have a problem simply that okay, I put the watch on and there's no phone, and the moment the watch is off me, the watch should stop collecting the data, right? In which case there is no all it is doing is it's doing your interrupt detection and no phone needed. That is a different problem than saying are the two devices on the same person. And right, I mean, two devices on the same person mean there should be. It's not about interrupt. It's about detecting something common between the two.
exactly.
Yeah.
So our
So
interrupt.
which one are you doing? Because the interrupt one suggests to me that you are looking for a change in who was wearing the device.
Okay, so if we're having, let's say we're walking and the phone is in our hand as well as a wearable, so we're looking for the common values to see whether they are on the same person, and the interrupt over here refers to the wearable getting detached from the person. That will show a change in the values. Based on that, we can certain whether it's on the same person or not.
So two clarifications or like two stages for the system. First is if it's on the same person, all of them on the same person, and the person is in motion. So that's why we have the velocity. So then we actually check that all of the devices are following the exact same velocity.
Velocity is not sufficient, right? I mean, I can forget both my phone and watch in a car. They have the same velocity, but they're obviously not for me. So it has to be some signature of the individual, right? I mean, the gait or the way. So there are two separate problems out here, and I think a complete solution has to have both. One is, are they on the same person on which the devices were initially authenticated?
Exactly.
Right.
That's one.
Okay, and and the other one is, are the two things on the same person? So these are two different scenarios. One is yes, I paired my watch and phone, and someone stole both. Okay, it should become disabled. And the other one is, I authenticated both and someone swiped my phone off. So watch is with me, the phone is with the other person. That also you should disable, right? These are two different scenarios. In one case, you have to detect that the two things are disassociated and with each other,
Right.
and in the other case, you have to detect they are not on the same person.
Yeah. So in that case, we can use a signature gesture.
So what is the signature that you're using?
The signature is the initial pairing to make sure like it's on one person. And so we ask the person wearing it on like the beginning in the morning, so they spell out their name, so we have like the speech to text recognition, and then we have it for like the wearable to have like that specific person's like gesture or like signature for the wearable. But then throughout the day, then we are assuming that all three pieces, like the hearable and the wearable and the phone, are still with the same person. So if the phone is moving at the same time, we want to see the exact like same motion for the wearable and the hearable. So if they are not following the exact same motion, then we will disconnect the sensor readings.
And your definition of exact same motion is what?
Like the velocity for now, to see if the person is, if it is
So
still
if I'm
following
on a
the
subway
same.
and someone swipes my earable off, it will have the same velocity, but it's not on me.
It wouldn't, and also like we are receiving
So you
the.
would not detect it, right?
That's true, but we have
Right.
also developed the heart rate detection on the phone and on the watch. So then we can also check that it is also on the same person.
I think you need to think carefully about the
Yeah.
cases out here. I don't think you're. Anyway. Anyone else with questions?
Yeah.
If you go back to the slide that had like a bunch of like sensor graphs. Wait, so do you go the next one? Or no matter
I think it's this one.
Also, Java, could you like use one of those sensors or maybe the accelerometer to like signal when the user left off your watch?
That's what we are trying to look at, like the data for the person. So we are trying to collect a bunch of like different data sets to see like for different motions how does the accelerometer data even looking like. So then we can detect if it's like the running motion or if it's like the walking motion. If I answer your question.
Yeah.
So you're just using the sensors to just for data.
To right now look at the data for detection.
Actually, what is speech to text recognition that you are talking about here?
So, for example, we're saying if this is the person or the owner of the device. So, for example, in the morning when you're pairing with the device, you would just spell out your name, and then that's how it just pairs up with the hearable to make sure it is on.
No, I'm not quite sure what is happening. Anyone can say my name, right? I mean.
Which is why, so we can combine that with another gesture, name followed by some other gesture, which, so anyone can say your name, but there might be another gesture which only you know, and you're going to use that gesture to validate that it's you. So we'll be using a combination of both because.
So it
not
syncs
just the
with
name.
the wearable. Once you say out your name, then it beeps in your ear, and then that's when you have to move your like wearable. So then after it detects your like
No,
a
so
specific
I
gesture.
say my name, and that is heard by what? By the phone or by the earable?
Earable.
Okay, and then what?
And then it converts to the text, and then that's how we see like, okay, if it matches our written string, then it creates that beeping, and then in your ear. After that,
Why is that securing anything? I'm not getting that part.
Because then you're the only person who is hearing the beep in your ear.
And then when you perform some other gesture, like anything like moving a hand or something.
No, so the purpose of this is what?
To make sure whose data is being recorded.
To pair the earable
and the wearable with the phone.
Earable and the wearable to the phone, right?
Yeah.
So you're saying I say my name, and then what happens?
So then the phone registers your name, and then after that it beeps in your ear. Supposing that you have the earable in your ear, and then after it beeps, then you have to play your signature, which can be like punching or like moving your hand, whatever you have registered. So if it detects that like a specific motion, then it will pair up with the wearable.
Okay, anyway.
Yeah.
I think you need to describe what is happening and why is this ensuring any security.
The details of
The details.
Okay, anyway, let's move on to the next.
Yeah.
Because like based on our discussions, we thought that it would be great to like have some sort of a factor that only the person can hear it out, but we can for sure discuss it more in detail.
Yeah.
Yeah.
You guys need a title for your project.
Yeah, looking at all other groups, I will realize like.
Yes,
Yeah.
we actually had one, but that was too long and too wordy. We're still working on a better one. So next time.
Okay. For our project, essentially what we are trying to do is we are trying to profile a program execution through the electromagnetic emanations. It's because when your processor is running some program, especially here we're looking at some loops. When it's running those, it will emit electromagnetic waves, and during a loop, your loop's execution time will be corresponding to a frequency that is 1/t. And looking at those patterns, hopefully we can find, like in previous paper, it has been shown like you can find some correlations between that emanations and the execution path. And so we want to, from our project, we want to profile which part of the program has been executed based on user input, because we are assuming that the program will be executing some paths instead of others based on the user inputs, and from that we can kind of decipher what user actually put into the program to trigger which part to be executed. And also we will also see the order of the execution based on the pre-run processing data. And then we're going to compare our experimental result with some simulation results from other papers, but for that we're just going to run the program instead of actually to build it by ourselves. First, so to start with it, we're building it for one platform for Raspberry Pi, and after we finish comparing our experimental result, we're looking to extend it to some more platforms, including STM32, Simple MCU, and Jetson TX2. We include that just because we have it in hand. Yes.
And before we start our research, we do some literature review, and we found that some papers present that spectral profiling is a new profiling method, and just detect the EM waves generated from the CPU or GPU execution process. And then we think about the possibility of this project, and we found another paper that some people have already do experiment on some GPU and on CPU processors, and shows that both active and positive EM wave attacks are possible.
So the math behind it is quite simple actually. It's just doing a short-time Fourier transform. So essentially what it's doing is just to put some overlapping windows in your whole computation. For example, if your computation is taking 10 seconds, then it will just put a lot of windows, like to window it to a smaller chunk and to do the short-time Fourier transform on it. And when you choose windows, like you can choose, there are some parameters we need to decide. First is the duration of each window. If you have a longer window, then you will have a better frequency resolution. But if your window is too long, essentially every window will blur all the activities inside the window into some frequency spike. So if our window is too long, it's longer than a loop, then we will not be able to observe those changing activities. So we want to have our so here what we're doing is we decide those windows experimentally. So we're starting with 100 milliseconds with 75% overlap, because with 25 millisecond precision, it is shorter than most of our loop operations. And after doing the short-term Fourier transformation, we'll be able to see the spikes of those frequencies spectrums. And by looking at the spikes and the shape of the spike, we'll be able to decide which path of the program is executed, which means what are the loops that is being executed and how much time each loop has been spent, and how many times this path has been executed based on the whole temporal structure, the temporal signal structure. So for our there are two phases: training phases and testing phases. Training phases essentially just collect all the data. So because without collecting it, we don't actually know what are each loops, how much time each loop is costing. So there are two ways to testing it. One with the instrumentation way, that is to set breakpoint in each operation. So we hit the breakpoint, then we do the short-term Fourier transform calculations, and then after doing that, we will rerun the program without all the interrupt, because with that interrupt in place, that will actually change our frequency a little bit to make our match not accurate. Then after doing the training phases, collecting all the data, we are going to do the testing phase. First, we are going to match the loops because from previous research paper, we find that with loops with interrupt independent spectra actually maintain their frequency spikes, so they can match it to be exact. And then after doing that, we'll, based on the information we get from those frequencies, we'll be doing our sequence-based matching for those non-input independent loops, so that we can tell which loops are executed, because we're assuming we know the operations of the program, so that we know which frequencies are being operated, so we know which loops are being operated.
And we want to we plan to do research on different platforms on STM32, Raspberry Pi, and Jetson TX2 and PC. That's represent a different kind of device. STM32 represent the mobile device, and Raspberry Pi is a typical MCU, and Raspberry Pi is also a kind of tiny PC. And Jetson TX2 is a GPU that manufactured by NVIDIA. And PC is include both desktop and laptop. And the hardware setup, as for hardware setup, we use two basic tools. The first one is spectral analyzer. It's used to analyze the spectrum, and the probe. It's a kind of the key part of the probe is antenna used to receive the EM wave.
Right. And next up, before we go deeper into our current progress, let me first introduce our tech model. As mentioned in many previous papers, as the data is being transferred in between different components of the system, those little electrical connections will act as unintentional antennas that will broadcast those EM waves into the surroundings. So what we're trying to do is to try to pick up on those EM waves and try to determine what the program is doing. And our program assumption is quite simple actually. At first, the program will have some sort of secret in hand, and then it will try to and then the program will decide which path to take based on that secret. And the way we can get what that secret the program is holding is by observing is by observing different EM waves produced by different parts of the program. Say, right now we right now we see a period of T1. That means this secret must be A, and if we're seeing a period of T2, it means A must be the secret must not be A. And we've actually written a simple proof of concept example. Like here this X is the secret we're trying to extract, and then the program will run two different loops based on this secret. And by observing by observing the frequency of the EM wave, we can determine which path the program has taken. And to further prove that the program is doing what we wanted, what we expect, we've actually taken a simple segment of assembly, and as you can see, this part over here is what we're trying to target. This little loop and the things that the program is doing inside this loop, we're trying to observe the frequency of this loop so that we will be able to tell what the secret X, like it should be shaded. Never mind. So this part will be our main target, and we can get to this target by observing these two loops over here.
But doesn't your microsleep take you back to the operating system? So it's not simply that this is
Yes.
everything. You also have
in terms of Raspberry Pi and those TX2, yes, and but as we mentioned, we are also trying to do this on a simple single chip computer and STM32. In those cases, it's just a bare metal system. When it sleeps, it's basically doing nothing. So I think under those scenarios, that will be better. And if we actually have an OS running, we can just do some more random things instead of sleeping. Like maybe do some more trash multiplication.
No, but since you're writing the test code, I guess all I'm saying is the following: this won't work just because you will have like for 10 microsecond you will have whatever the operating system decides to do, right?
Yeah.
So why do this?
So I think from the papers we're reading, like the reason we're trying to sleep here first, it is simple. The second is showing if you have a very simple operating system going on with the bare metal ones, not running other intensive tasks, those switching tasks doesn't affect your result much because of the operation it does will not be affecting your final frequency much. So it will introduce some noise for sure, but it does not affect your results fundamentally if your operating system is simple enough, which is what we're employing here.
The major frequency should stay the same, but the harmonics would change if we have an operating system involved. Yep. And as for our next steps, we have first identified two major challenges. The first one being the data might be cached. In that case, there won't be much transfer happening, so that there won't be enough antenna to send out those EM waves. And the way we plan to deal with that is to first perform a cache flush, so that the data will have to be moved from the memory to the cache, so that more EM waves can be produced. And another challenge is if we have a constant register value happening, there won't be enough bit flipping, so not enough EM wave will be produced. And our solution will be to read some pseudo-random sequence, so that there will constantly be bit flipping, so that there will be enough EM waves. And so more precisely, we first plan to secure some measuring devices, for example, a probe or a spectrum analyzer, and then we will run our code on those aforementioned platforms, and then we'll start our profiling and try to extract the secret from the program. Yep. and that's it.
So what's the difference between what Georgia Tech folks, I mean, we had this guy as a
Yeah.
candidate, right?
Yeah.
So what's the difference between what he has already reported?
So
what you're doing?
essentially, what we're trying to do is to just reproduce, implement his ideas. Because at the beginning, we were trying to say whether we can actually steal some secret data, but from reading those papers and from our experimental result, like from different 0-1 operations, like we cannot right now we cannot sniff all those data. So we made the assumption like based on the user input data, different loops will be executed.
Yeah.
So
At first, we actually thought about trying to just trying to attack the data directly, but then in that paper, in the paper we mentioned, the second one, they actually did those. They call those value-based experiments, but they said that the result was mostly negative. So we decided to go with the other one.
Cool.
Any other questions?
And we are planning to optimize the probe. I mean, because the receiving the EM signal is also very important. Yeah, we are trying to make our own antenna.
Also, make sure your understanding of the underlying process is correct, because from his talk it appeared that the reason EM waves are observed and what the phenomenon he's observing is because the clock signal gets amplitude modulated, and that's what is being picked up. It's not the bit flips and all.
Yeah.
So you might want to look through his papers again.
Sure.
Okay. So it's not simply if a value is being transferred, the bit flips which is happening. That's not.
Okay.
At least my understanding.
Right.
Okay, but make sure to very clearly, like, what is it that is it just reproducing his work or something else?
So far what we have done is reproducing. If we want to be creative, or if we can be more creative, can come up with some ideas to give some interesting scenario, we will. Cool. Let's go.
Thank you.
Thank you.
Okay, so we are done for the day.
Oh. Right? No. Oh.
Yeah.
You are one more.
There are
Oh,
two.
I'm sorry.
Yeah. Somehow I thought they were on the Z's,
yeah.
so we were.
No.
Oh.
Well, I'm Julian. I will present today my work in guarding against screen contact detection via remote acoustic side channels. I'm based totally on a paper called Synesthesia, detecting screen content via remote acoustic side channels, that was published in 2019 by Daniel Genking and others. No, so which is the overall project goal is to prove that it's possible to guard computer laptops with LCD screens against this discovered acoustic side channel. By concealing this sound generator. No? The specific aims are first, well, to analyze the frequency spectrum, in this case of my laptop, and see if it's vulnerable to the attack. Then to process the audio signals captured and try to obtain samples that are representative of what I need to explain is that, how LCD screens work is that they have a refresh rate, and in each cycle of that refresh rate, the image is rendered. So what we need to obtain is a sample that's representative of one of those cycles, no? And for that, we need to process the signals and average some chunks in order to obtain a sample that hasn't that much noise. No. After all that process is made, we need to train a convolutional neural network with those samples, so we can, in this case, distinguish between different websites that are being displayed in the LCD screen, in the computer. And lastly, I'm not sure if I'm going to get to this point. My main point right now is to replicate the experiment, but if there's time left, I want to test if it's possible to guard against this attack by either masking the noise, the sound generated by the LCD screen, or to actively cancel it, no?
So how does this work? First, we need to obviously record the sound. I'm recording it at 96 kilohertz with the integrated microphone in my computer. And what I need to explain is that the researchers that made this paper found like 2 frequency ranges where information was filtrated. One was in the range from like 2 to 3 kilohertz. And in that range, the signal was correlated with the brightness of the pixels. And in the range from 20 kilohertz to 30 kilohertz, what they found is that it was a signal, an AM modulated signal, that when demodulated, it correlated with the color of the pixels. What I found when analyzing the spectrum is that the signal I got in that range, from 20 to 30 kilohertz, the range where the researchers focused in all the paper, is that the AM signal I got didn't have any carrier. So I was dealing with what I thought was an AM double sideband signal, carrier suppressed signal, suppressed carrier signal. And so first to try to demodulate the signal, well, I used a Costas loop, that works as a carrier recovery and also demodulates the signal. So afterwards, when you already have the demodulated signal, you need to divide the signal by chunks according to the refresh rate, because in each refresh cycle, as I said, the image is represented. But what they found also is that the refresh rate isn't static, like it's constantly changing by either drift or jitter. So you need to have a more or less complex algorithm to try to see which is the best chunk size. And then with that size, try to average many of those chunks in order to obtain a representative chunk that has lower noise, and that serves as our input to our convolutional neural network classifier, which has a softmax output layer with in my case, I'm testing with 5 websites, so it has 5 classifications, no? So the current status, the laptop does leak the signal. Here's a spectrogram of my my computers of the sound produced by my LCD screen. It's bandpass filter, so you only see the band from like 20 to 30 kilohertz. And you see that it has the 2 sidebands, but it doesn't really has a carrier, so it's a problem I'm trying to figuring out. Well, the Costas loop is already implemented. The denoising algorithm also implemented. I already have all a good amount of audio samples obtained by automatic process of obtaining samples from websites, 5-second samples of each website visited. And basically the next steps are to try to adjust the parameters of the Costas loop and the denoising algorithm, because the final average chunk that is used for the input for the CNN network isn't that it has a lot of noise, so it has been a problem there. Then maybe develop the noise cancelling or noise masking algorithm, and then if you figure out, I was only talking about this range from 20 to 30 kilohertz that is the main focus of the paper. But they also mentioned this range from 2 to 30 kilohertz frequency range, and they also try to use it in one of their use cases. They don't really develop that much, so I was thinking of maybe also trying in that range to see if it serves like a better it works better, in order to classify the content produced by showed in the screen. That's I don't know, questions you have?
Questions, anyone?
No.
So the paper you mentioned, do they also use some built-in microphone from a laptop, or do they use some other microphone?
Yeah, well, the paper says clearly that you can use your built-in laptop microphone. In fact, any webcam, any smartphone. But in reality, how they made all the experiment is with a very high-quality microphone. No, like they do all the experiments with this. Well, more than the experiments. They show all the experiments with this high quality microphone, and they only tell that some of other experiments they use like the built-in microphone. But yeah, it's like kind of weird, no? Weird that they have to use a high quality microphone to, like, I don't know, to do much of the experiments. But yeah, basically it.
So what's the underlying physics like?
Okay. So the LCD screen has a power supply, and the power supplies apparently vibrates and produces this sound, and it depends on the changes in the intensity of the pixels. So it's apparently a complex relationship, and that's why they use also a convolutional neural network, because they don't have really the exact model. I don't know. They can model it exactly, and they have But
So is the end result that you are able to reconstruct what the average intensity is right now, or do they actually get the screen content?
Yeah, they got which website the victim was visiting, but they don't know exactly what was in that website. No.
Okay. Any other question? Thank you.
All right, hi guys, my name is Michael.
My name is Vyacheslav.
And our project is on creating an adversarial patch robust against visual deformations. So this is just a quick outline of what we're going to go over. We're going to go over our overall project goals and specific aims, as well as a quick introduction to the adversarial patch. And we're going to talk about previous works and the novelty of our project. In our technical approach, we're going to talk about how we're folding and physically deforming or visually deforming our patch and training our algorithm, as well as the platforms we're using, and as well as our current status and the next steps. So our overall goal is to create an adversarial patch robust against folds for adaptability in the physical world. And we specifically want to create an algorithm to train our adversarial patch, and we want to be able to determine how accurate or how inaccurate our patch can make our training set and test set, as well as evaluate the performance of regularization techniques that we can use. So just a quick intro on the adversarial patch. It's gaining a lot of popularity and because of its feasibility and practicality and in the real-world computer vision system threats, and attackers do not need direct access to it. They can just use a sticker or a patch to attack these object detection systems. And you guys have seen like the pandas, obviously. And this is just an example of how an object a system can recognize a person, but not a person with a patch. So previous works on the adaptability of patches include translating the adversarial patch, rotating it, changing the brightness of it, and scaling it as well. There also exist physically printed adversarial patches, such as a t-shirt, hats, glasses, and these are also specifically to clothes, and the hats are subject to wrinkles and folds and other visual deformities. So that's what our goal is. We want to be able to explore these types of patches that we can make adaptable to such physical changes.
So we divided our work into two main parts. First of all, we wanted to prove that our task is feasible, like at all. And then we are aiming to optimize it. So to prove that design of such a patch robust against wrinkles is possible, we implemented a classic gradient descent algorithm And as a model of fold, as a model of wrinkle, we use just a fold, a bit on the later, on the next slide. So sorry. After doing this experiment, we are going to perform several other experiments on optimizing this patch. We firstly introduce more complex permutations, not like just a simple fold, but something more realistic. We will also increase our training and test sets and implement several regularization techniques we read recently. So this is how we are modeling our wrinkle now. It is just a simple fold. So we just take part of the image and cut it off. And we are thinking that if our patch is able to survive this permutation, it will also survive some minor changes. We are going to model a bit later. So for our project, we use TensorFlow. As data sets, we implement ImageNet. And our image classifier is Inception version 3. So about what we have already completed, we implemented this classic algorithm. We showed that it is possible to get an adversarial patch robust against this kind of fold. We are actually able to delete up to 20% of the patch. We are able to shift it in random place and attach it to like any image. But currently we don't have results for the test set, but for the training set, accuracy is 55% worst case, and the current patch size is 3.5% of the area. So this is basically TensorBoard representation of our algorithm. Here is the patch. Here we shift it, fold it, and attach to the images, and then process softmax classifier. And basically, this is how we get our loss function. Our loss function is cross-validation error for our target class. We wanted to misclassify. So this is our patch. There you can see a patch attached to image. So accuracy is not like 55%. It is not so high, but the closer you are to the center of the image, the better are your results. And anyway, we are going to play a bit with the size of patch and to see the trade-off between accuracy and size. This is what is going next. We will use regularization techniques to improve accuracy of our adversarial patch. We are going to employ more realistic type of folds using using TensorFlow API, and and we gather more images from ImageNet to train on. So this is our references, and if you have any questions, please ask.
Anyone questions?
Yeah.
Do you have any constraints on the patch size? Because like you could hold a shield of the patch and then cover your entire body, but I think that's not what you're trying to do.
So as you or maybe you okay. In our work, patch size is currently 3.5% of the image area. Other implementations, they have different sizes because they have different constraints. For example, if you survey the works currently in this domain, shift does not dramatically increase patch size. But if you want to be robust to scaling, your patch size increase dramatically. This is why in the example we have shown these guys have this patch this large because they testing against camera, and this means that the patch should be robust to scaling when you move towards and backwards on the camera.
In some cases, when you move the patch around, won't that itself create a misclassification? Like, irrespective of whatever the patch is, like in the picture you mentioned.
In this picture.
Yeah. So suppose the patch would be somewhere close to
The center.
cat's head.
Yeah.
Yeah, it's more accurate.
Consider those cases.
No. We are able to. We are robust to that. So if we move patch from here to any place on the image, actually accuracy can only improve, especially if you move toward the center.
Yeah, that's what I mean. So.
Sorry. Can you? This is what you meant.
Yeah.
Okay. Yeah. So yeah, we are training randomly sampling at this patch at different locations of the image. So we are robust to that. Yeah. Anything else? Thank you.
Okay, see you guys on Thursday.